recent talk probably heard about, which is SIMD programming. I'm CTO of Numscale, which is a small French company that deal with high-performance computing and performance in general. And we have these specialties of trying to do most of our works and software in C++, and trying to be as bleeding edge as possible on this front is one of our mission. We also try to be involved into the C++ community. We are part of the French national body for the ISO, and we sponsor a couple of conferences. And we try to give back to the community through our open source work on different fronts, including Boost. So why are we there, actually? Well, let's start with a simple question. What the heck is SIMD? So I usually do this, so let's start with a small poll. So who actually cares about performance in his daily jobs? Okay, yes. So yeah, and then, so some of you probably heard about parallel programming. Yeah, pretty much the same. Okay, tough audience. So I guess some knows about SIMD already. A bit less. Yeah, not that much actually. Oh God. So those acronyms probably ring a bell. Okay. And so you probably know that you have nightmares because of that. Yeah, you can. I do. So yeah, yeah. So it's actually interesting. It's a very different sampling than what I got at CPPCon, but well, it would be interesting. So for those that didn't raise their hands past question 4, this is what SIMD is all about. So let's say you have some workload to process, okay, and you want to process this workload as fast as possible. You could actually do a lot of things, including getting multiple processors or multiple machines to collaborate to do these workloads. You can try to shove that into a specialized accelerator, but most of the time you start by using a single regular CPU, which has the good idea to give you, let's say, one result every CPU cycle. Okay, so it takes some time to process everything. And another way to do it, which is it's rather funny because, I mean, SIMD programming and mostly SIMD hardware are a very, very old stuff, but a lot of people doesn't really want to deal with it, so it's a bit obscure somehow. But you could get a SIMD-enabled CPU. It looks like a CPU, just a bit different, okay, like wider or something. That lets you actually process your workload in a SIMD way. That means that every CPU cycles, you get multiple results at the same time. So it shows that you should have enough workload, so using this kind of CPU is worthwhile. And, well, your data actually still has to have verify some constraints. So if not, the CPU doesn't want to work correctly. So in a less cuisine-like approach, what's actually SIMD? So SIMD extensions are a small subset of instruction that lies into most modern computers since, well, the end of the 90s. And the main idea is that whereas a regular CPU processes registers that contain one data at a time, SIMD instruction set provides what we call wide register or large registers, in which you get up to 2, 4, 8, 16, 32, 64 value at the same time. And every time a CPU clock comes in, you get a single instruction in, and this single instruction will be applied to every element of your wide registers, and you get a wide register of results. So if everything goes right, so the code is amenable to be written, so this pattern appears, and if n is big enough, and so on, you can get a significant speed up, which usually will be roughly proportional to the, or you expect it to be roughly proportional to the width or the cardinal of the register. It's quite nice because depending on what you do for a living, it can prevent premature scale out. So instead of buying 10 times more machine again, you can just go 10 times faster on the same processor by using this, something that we may be not doing already. and it makes the flops to watts ratio a bit higher because you are really using all your CPUs, and it goes faster for probably the same amount of energy going in. Okay, so that's the cool things. You got registers with this wide amount of data inside, and if everything is cool, you get that much faster. But the problem is, looks like everybody got the same idea, being Intel, PowerPC, ARM, and some others. And they got the same ideas, different times, different places. So basically everything in those bullet lists is mostly not compatible with the others. So Intel started the dance around 1996, 1997 with MMX that get quickly replaced by SSE, SSE1, SSE2, SSE3, SSE3, that's not a typo. And then AMD came back, and then it was SSE4. We went to 256 bits with AVX, AVX2, which has added support for the integers. And now we will soon get 5112 bits with AVX 512. So it keeps growing, and you have all of this available. PowerPC has its own things, AltiVec, and the new version of AltiVec for the Power 8. ARM has a different number of stuff, but the main one has our Neon, which is what you can use right now, and you have much more than that. So what happens is that usually people pick one, which corresponds to the kind of hardware they want to target. They become very efficient with this, and they have a very hard time going elsewhere. And even if you say, okay, I'm just dealing with Intel anyway, or just with Neon, well, at some point you got some version on, but 6 years later you have something which is like probably twice faster, and then twice faster again. And the cost of actually going from one of this to the others can be cumbersome. It can be cumbersome because most of the time, the code you have to write is completely different in terms of naming scheme and whatever, and function names and functionality, and it piles up quite a lot. And if you want to be efficient with all of that, it's quite difficult. So, how can you actually take advantage of those? Well, either you rely on what we call implicit vectorization, which is letting the compiler do its job, because actually writing efficient code for a given subset of instruction set into a CPU sounds like a compiler job. And autovectorizer do quite a good jobs. In all the cases, they do a good job, okay? Thing is, the amount of cases they do a good job keep increasing. It's a very active work area, and there is some really mind-blowing results on different compilers. And if it doesn't fit, or if the compiler is still a bit confused, you can help him by adding some keywords, some pragmas, so you can help the compilers do its jobs. And on the completely other side, you have explicit vectorization, where you actually have to write your code so the compiler knows you want vectorization there and in this way. It goes from language extension, intrinsics library, intrinsics themselves, that's what most people do, and, well, inline assembly. So for the sake of discussion, we just forgot this last option now, okay? That's not something which is neither sustainable, neither, it was the worst portable options in all of that, and, well, no, you don't really want to do that anyway, right? So let's forget inline assembly. So we stuck with this. So what kind of trade-off can we get on this? Well, implicit vectorization rely on dependency analysis of your loop nest, which means that you need to have a loop nest. It recognizes patterns, idioms, and it turns your code into something that will be very fitting to this. If you call a non-inline function in the middle of your loop, and this function is not recognized as something the compiler can actually call into a vector context, well, you fall down to scalar. If you have multiple nested loop, most of the autovectorizer will try to vectorize the outer loop, the inner loop, sorry, and you won't have support for outer loop vectorization, which is the correct things to do sometimes. and your quality of vectorization depends on the quality of the auto-vectorizer. So even if you have 2 or 3 different compilers that support auto-vectorizing the same piece of code, you may have difference in terms of performance. On the other side, when you deal with explicit vectorization, well, there is no analysis whatsoever. You are telling the compiler that the SIMD part is broadly there. You don't have to care about data dependencies because you are forced to write your code in a way those data dependencies has to be fixed by you. You can vectorize non-inline function, and you can vectorize whatever loops you want. And sometimes, and I will emphasize this on sometimes, it may be more portable than the automatic vectorization. But then now, you're not dependent on the compiler QOI, you are dependent on the explicit vectorization tool QOI, which may or may not be better than any other solution. So it's a very wide area of work. There is plenty of stuff going on right now, and there is no clear-cut solution, and that's not something I want to it's not a statement I want to make. So in this context, what we think is that explicit vectorization has one big advantage, that you can actually make it so it will look like regular, good old sequential scalar C++. You can merge with modern C++ idioms using algorithms, using ranges, for loops, whatever, and still get performance out of that. And what we wanted to do is to show that we can actually do that. So we worked on this for quite a while now. The original basic codes came all back from 2006 during my PhD thesis, and it has been rewritten countless times for now. And we ended up with what we call BSIMD and BoostSIMD, which is actually this. It's an explicit vectorization library written in modern C++. The goal is to provide a way to abstract most of the complicated idioms and way of writing codes when you want to write SIMD-enabled code in a way so that you can actually write your vectorized code once, and you take it on whatever architecture you want, you recompile, and if it compiles, that means that, yeah, you will get some amount of performance out of it. And you don't have to care about what's the frigging types names already, what's the operation I need to be doing there, what kind of constraint I need on my data, and so on and so on. We take care of all of that, and you just care about writing your actual domain-specific, application-specific code. So BoostSIMD is actually an open source sub-segment of BSIMD, which is our main product at Numpscale. It's basically support for x86 and PowerPC up to 7, with a bunch of STL-like algorithms thrown into the bunch. And so you can actually quickly build SIMD-enabled application on those kind of architectures. So how does it look? The main abstraction we need is basically finding a way to abstract these kind of things. So this is a neon piece of code that multiplies 2 signed 32-bit integer. Fine. And this is the same code for SSE4. Fine. Okay, the names are funky, but it's okay. And then, okay, what should I do for SSE2? Well, you need to pray. And the worst is actually, when you look at that and you know what it's doing, is clearly trivial. It's basically what you learn at school when you learn to make multiplication by aligning numbers. So that's basically a multiplication made 32-bit by 16-bit by 16-bit with a carry-on going over. Okay, that's exactly what it says. Okay, right? But, well, it could actually get worse, because at some point you need to go on VMX. It's the exact same algorithm. The exact same algorithm than that, as you may see. Okay, I spent 1 month on that 10 years ago to get it working, so, well. Well, when you don't know what you need to do, I mean, it could be complicated. So everything is different. You have different rules for what you can do. I mean, yeah. So you don't really want to shove that into a simple pieces of macro or whatever. You need an abstraction level on top of that. So what we provide is these types we call pack. A pack of T is of Tn actually. It behaves a bit like std array. It's a bunch of value of type T. You have got n of them, except that for every given couple of T and n, if I know an optimized way using SIMD register to store this data, this is what I will use. So there is an additional constraint compared to std array, that n must be a power of 2. Can be 1, but it has to be a power of 2. And T is currently just a fundamental type. And we will pick the optimal types depending on T and N. And, well, it's rather trivial. I mean, let's say that C is the current hardware register size that is the most efficient possible on the given architectures. If N is equal to C, we just use this native register type directly. Okay. If it's smaller, currently we are using a scalar array that's going to change really soon by actually using a native register with a mask. And if you are bigger than the expected size of your local register, we will just aggregate 2 pack of Tn over 2. And this recursively until we found out our native register types. So this means that you don't have to care about what machine you are on. You decide the size of your pack. If you don't put n, and you just make a pack of T, you end up with the most optimal size for the current hardware. I saw a question. Sorry, I got the light there.
When you say current hardware, yeah, when you say current hardware, is that a compile time decision or is it a runtime decision?
It's compile time. Okay. Everything is compile time. I should have started with that, actually. Everything is compile time. So it means that if you change hardware, you need to recompile. And I will go over the runtime selection of variants of hardware a bit later. So, which means that most of the time what you want to write is code ending with pack of T and be done. You have a bunch of constructors on pack, okay? Either a splatting constructor, you can enumerate every value into the pack. You can store from an aligned pointer, you can store from a range that doesn't even need to be contiguous. And you will also have explicit memory loads with and without offset. And if the offset is not an integer, but a vector of integer, you do a gather. You will pick up values from the base address plus every value of the offset and bring it into a pack. We split up on load and align load, so you can actually optimize the cases where you know that your pointers are already aligned. And same for store. A bit later, we have everything back for store. And we also support what we call static misalignment. You know you are loading from a misaligned piece of memory, but you know exactly by how much you are misaligned. That's something that came across a lot of time when you write discrete filtering. You know that you want this value, the one before, the one after, in a sliding window. You can actually optimize this by using a line load with a static misalignment offset. And it usually generates better code in terms of performance than just making an align load. So same for the store, and same that for load. If you store using a pack of offset, you do a scatter. We also support pointer and mask pointer, so you can actually store and load from a masked with an address with a mask that tell you where you want to write or not. So when I got this pack, what can I do? I can do whatever I want with it. We have support for every basic operators, more than 300 functions. We do comparisons that give you back a pack of logical value. And you can compare packs, so you get a Boolean. A pack is also a random access range. It has the exact same standard interface as std array. So you can iterate over each element of the pack using begin and end and so on. and you have an access to the nth element from the pack quite directly. So this is a selection of functions we have inside, so we got a bunch of them. Most of the libc math function, a bit of specialized EIII operations. We have a bunch of predicates that are already optimized. And we have a lot of reduction, so you can check for predicates over element into a pack. And we got a lot of what we call swar operation, which is basically every swizzling, shuffling, reorganizing of data inside the pack. Okay, so, and in all those operations, one very interesting is this shuffling. Most of the time, you end up with a scalar code where you have to, look at it very, very for a very long time, because it doesn't look like something that can be vectorized, because the memory access pattern is complex. But sometimes you find out that this memory pattern can actually be turned into, I'm just loading data regularly, and I will shuffle them into a pack I will work on later. So this data reordering operation is usually the most variable operation you can make to make a code vectorizable. It deals with transposition of data, turning an array of structure into a structure of array, and the other way around. You can turn arbitrary memory access with a static pattern into shuffling. And, well, you have a bunch of pre-made permutation, like you can reverse, you can broadcast, you can merge two packs, or you can unmerge them. Or you can perform repetition of sub-element, slide the whole pack, or you can make runtime lookup where you pass a vector of index and you reshuffle everything. But the most interesting operation is when your permutation of data can be expressed as a compile time system. In this case, you can actually optimize this shuffling. So if you have an arbitrary permutation at compile time, you can write stuff like this. So let's say you have two packs, okay, or 4 floats, and you can call the shuffle function that takes parameters, which is a series of index. So we tell you, okay, I need to take the twice the first element and twice the last one, so R1 will be equal to 1, 1, 4, 4. I will pick up 1 twice and 4 twice. And you have a special value, which is -1, that say, okay, I don't care about what gets there, just put a 0. Which is something that is potentially optimizable on a lot of hardware. And if it's not, we just mask whatever we need to mask. So we can do this. But the problem with that is the shuffle call depends on the pack size, which makes your code maybe less portable across architectures. So we need the way to say, this is the way I want to shuffle things without having to explicitly enumerate them. So the old way of doing it was to write an MPL-like meta function that was taking 2 integral constants as types, as the parameters, and you were computing something like this. So that's reverse. So whenever I want to know where the number I index goes into a pack of cardinal C, I know that if I want to reverse it, it goes to C minus I minus 1. And you can just pass this type to shuffle, and it will automatically generate the proper permutation. Okay, I think that on the scale from 0 to never, the elegance of this solution is very low. I mean, you need to have your user to write a meta function, so you already are, like asking for something very complicated. That's what we got before C++11. In our interface, we just keep it for consistency sake. But now what we can do is better, because what do I do there? I'm computing a sequence of value at compile time. So that's what context per function are for. So you can just write a context per function with the exact same interface, current index, size of the pack, and this is how you compute the new index or where you want to go fetch your value. And you just pack this context per function to shuffle using the pattern constructors there. And you just do whatever the old one was doing, except the only thing you have to write is a regular-looking context per function. Okay. So I wish I can get rid of pattern, but Visual Studio keeps confusing a shuffle of 0 between shuffle call on an integer and shuffle call on the null pointer to this kind of function. So I need to put that into a box. I don't know if there is anybody from Microsoft over there. Yeah, he was not paying attention. So yeah, so I have a bug to report over there. But whatever, it works. So you can just write your complex shuffling stuff into a context per function and shove it there. Just works. So that's very interesting. But sometimes different platforms requires your shuffling pattern to be very specific to be optimized. SSE2 is well known, so you cannot shuffle value across the middle of the pack. So we do perform checks and rewriting of the shuffle, so most of your shuffle end up optimized. Okay? And we recognize a bunch of patterns. We also have a lot of algorithm and range that just work with the STD library. We have a SIMD version of transform and reduce that use generic lambda for doing the computation, and we have a bunch of range, which are rather explicit on what they do. Input and output range with or without alignment, and with or without segmentation. I will get on that later because that's very interesting things. So you can just write code like this. You make a vector of float using our SIMD allocator, and you just transform it from the beginning to the end. And you use a C++14 generic lambda, and this thing will just slice the data, okay, into the properly aligned for vectorization part of the data, and a potential epilogue and a potential prologue, and we call this generic function on each part. The function being generic, it will call the scalar version of the function on the epilogue and the prologue, and we call the BoostSIMD vectorized version in the middle data. But that's just what you have to write to just, vectorize your transform. Same for reduce. With the only change that when you want to do something complicated, like for example, you want to compute the sum of the square of your elements, you cannot reuse this function as the final reduction step. You need to just make a rigorous sum. So we have a way to specify that if you have a special binary accumulation stuff that needs a special treatment, this is what you want to do at the end. And if you don't do anything, we behave like the classical accumulate, and we perform that. So how does it work behind? So we have like 4 different architectures with something between 2 to 10 different sub-architectures instruction set. And depending on that, and depending on the type of your data, the optimal implementation of your SIMD code may differ. So what we use to quickly and properly select the correct implementation of a given function is to use an augmented version of tag dispatching. So tag dispatching is a well-known classical generic programming technique that consists to map types to a family of tags, which are types that describe properties of other types. And when you do this, you take your parameters, you compute the tag, and you use regular function overloading to jump to the correct position. That's basically what is done into the standard library for dealing with the iterators, variability of algorithm implementation, and so on. So what we do is that we take that and we augment it with a family of tags that describe the function properties. A function is actually a function object in BoostSIMD, and we know that, for example, plus, it's an element-wise function. It works on each element separately, while sum is a reduction, and while cumulative sum is a scan, and so on and so on. So we can access information about the kind of function we want to run on. And we have a tag that describe the current architectures. And every architecture that has an ancestor has the same architecture tag as an ancestor, so you can just write a function on SSE2 and on SSE4, and if you call it on SSE3, it would just fall into the middle and gracefully fall into the SSE2 implementation. We did that instead of using SFINAE for compile time issues. So basically what we say is, I clicked. Thank you. So we have this function plus. So plus, as I say, is an element-wise function. So it's basically declared like this somewhere. And so the function plus and the operator plus just make a functor out of this tag and call whatever you need to call on this. And what functor does, well, it takes whatever arguments it needs to. It takes something that we call the site, which is the type that describes the current architectures we are compiling for. And we compute the tag, what we call the hierarchy, of every information, the architectures, the function, and every argument we have. And we put that into a box that we call with all the arguments. I probably should std forward there, but that's just an example. And those dispatch box can be defined like this. So if I dispatch something when I'm using SSE2 and I'm trying to resolve what plus should be doing on types which behaves like a SIMD register containing a single precision value with a storage which is compatible with SSE, well, probably means that I can do that. Okay, and we do this for every kind of operations, architectures, and sometimes we can use that to be able to optimize some stupid cases, like you are computing absolute value, so you probably have an implementation for floating point values, and for signed integers, and for unsigned integers, I can just say, okay, if it's unsigned, I just return what I get in. So we use that to specialize across function types, architectures, and parameters types. And we let the system pick the correct function for whatever combination of that. And everything is picked at compile time. The other stuff we did was, I was speaking about this segmented range. What does this segmented range do? It takes a regular range, and it gives you a tuple of 3 range, the part that you need to process in scalar before you end up having a first line data that you can vectorize. Then you have a second range which is all the vectorizable data pack that ends before the end of the original range. And then you get the epilogue, which is basically whatever scalar are left after the last place you can vectorize. And so you can actually, this is the actual code of reduce. So we start putting a 0 into the accumulator. We compute the segmented range from first to last. And what we do is we start accumulating into init in a scalar way. Then we accumulate in ACK, but ACK is a pack, so this is done as a SIMD operation. And the range from get1 of PR is actually a range that gives you pack every time you iterate over it. So the second loop just gets over the central part of the original range, pack after pack. And then we finish by computing the remaining scalar accumulation, and we finish by adding the scalar value to the sum of whatever we found into the SIMD accumulation. Before segmented range, this exact code in the very old version of BoostSIMD was probably 6 times bigger, because we had to compute all this beginning and end of whatever. And getting this range abstraction was very useful because most of our standard algorithm implementation just look like that. We compute a segmented range and we go over. So it's a bit more complicated when you have a generalized reduce with a potentially different neutral element for your final reduction. So it looks the same at the beginning. And at the end, what we do is we accumulate every element of the accumulator, which is a single pack. So we just go over every scalar into the SIMD registers. And we call the final R function, the final reduction function over it, the same way we do that on the other segmented range. So we take a range, slice it into 3 ranges of different types. We accumulate over them, put everything in, and then we have a pack with all the results that we keep. We finally reduce itself before returning the value. And everything there is automatically vectorized because the values that get out of the middle of this is a pack, and pack operation gets picked up, and everything gets vectorized. So before speaking of performances, I just want to show you some other things about the implementation. So I don't know if is this big enough. Is it? Okay. So I spoke about reduce, so yeah, that's the actual code, okay, so it's not even a marketing ploy, so that's actually what we wrote. And transform is basically the same. The transform is a bit more complicated in some cases. So the trivial case with a unary operation basically starts the same. We segment the range, okay, and well, segmenting the input range is easy, but what do we do with the output? Nothing tells me actually that the output is aligned or not aligned, and if it's not aligned, nothing tells me that it's not aligned the same way as the input. So what we need to do is we look at the actual output pointers, and if it's aligned, that means that we can align store directly. Okay, so we walk over the vector parts by actually storing in an aligned way the result of the function applied to every pack into the central part of the first range. So just before we treated the prologue there using the classical scalar way, and if the output is not aligned, well, we could go into very complicated stuff trying to find where an alignment ends up, but it's faster and simpler to just say, okay, if everything is unaligned on the output, I'm just storing using the unaligned store functions. And then we end up finishing the transform by, well, just getting another pass of scalar stuff. It looks a bit convoluted. It's a lot of high-level operations. In the end, the result assembly code we got is basically what you have if you've written the whole things by hand. Everything gets smooshed out by the compiler. So this is a completely zero overhead operation. Now, getting back on this tag dispatching stuff, we needed this augmented tag dispatching system so we can actually have a way to overload function on arbitrary set of property of types, which sounds awfully like concepts. So my wish, or my dream at some point is that we can completely ditch out these tag dispatching systems whenever concepts are in, and using concepts. We made a very rude prototypes with Andrew Sutton of turning all our tag dispatching family into equivalent concept and trying to rebuild this. And well, it works on the paper. We just need now compilers to actually support that. Probably shove a lot of boilerplate code out of the code base. What can we do as a funky things with this generalized tag dispatching too is, what if I write a code where P is a pack, and I wrote something like P plus 3, where 3 is an arbitrary scalar? Or what happens if I call a function on a pack, and the function, for whatever reason, on the current architectures is not vectorizable with whatever intrinsic you have, and the only thing you can do is slicing the pack, scalar by scalar, and filling it? Well, if the function is an elementwise function, we have a clear system to do that. Well, it's a bit verbose, but basically what we do is, where is it? All right, let's start with this one. So you have an arbitrary number of packs going in, Pn, and you apply an elementwise function on it, let's say plus. And for whatever reason, you don't have a vectorized plus on your system. Bad news. What happened is we jump into a function that say, okay, what you need to do is just to build a pack where every element, for all the elements inside the pack, are what? Are the function called on the nth scalar element of the pack for every argument of the function and for every element inside the pack. So we use this good old pass and integer sequence as the parameters to get an expandable template packs there, so we can statically iterate over each of those sub-elements in the pack, which means that these things is usually turned into a single call to the equivalent vectorized pack building operations. And this combination is actually funky because we are dealing with Parameter pack expansion in a generic function that ends up calling vectorized operations, and everything played nice, and we end up with exactly the code we want to do. But how do I know I can go there? Well, that's where the tag dispatching of the function is interesting. So if you end up to have, well, you have an overload on an arbitrary Elementwise function on an arbitrary architectures, and you have an arbitrary number of packs in, then if you weren't picked up before, this means that if you verify all of this, you will fall into this case. The gunk before the actual operation are just generic codes that compute what kind of pack I'm supposed to be returning, and the pack I need to return is a pack that contains a type, which is a result of the function applied to the corresponding scalar value of each pack. We check that we have packs of the same size, and so on and so on. That's rather straightforward. It's a big verbose, but we are able to have this level of control of what's going on. So we can check, the types, the size, and so on. And if everything is okay, we just build this ever-expanding pack threads, template parameter packs done. There is one thing I really want to do there, and I don't know how. So if you want to win a trip to a restaurant, okay, look that I'm forced to iterate manually over the number of packs into the function. I have the unary function, the binary, the ternary, and the quaternary function. Why can't I have a second template variadic pack there so I can unroll the pack number and then unroll the size of each pack so I can write something like, result type of f of p brackets n value dot parents dot inside. I wasn't able to do that, so if you have any idea, I'm very welcome to hear what you want to do. I think it's non-trivial, and I think it's not possible, but if you know how to do that, I'm all ears open. Last stuff which is actually interesting to do is, nope, it's not that. It's look at how this can actually be also applied to another subset of things. But as I say, this is the absolute value implementation. So if I don't know what I have, but I'm dealing with a absolute value of an integer types, well, I'm just returning nothing. I mean, just returning my input. I mean, I have no work to do. Done. And if I'm signed, whatever the architectures, if this architecture doesn't already have a more specialized version of this absolute function, I end up there and I just, compute some stuff to get the sign bits and trigger it and whatever. And if not, the other way to do it, if I'm a floating point value, well, I'm just calling some bitwise tricks between the value and -0, so it triggers the sign bits. And look that we have something new there, which is this is native of x around there. These kind of threats help us to know where we should be going through those common implementation. There is two cases we don't really want to do this because it will generate very bad code. Is when we end up with what we call an emulated pack. Emulated packs can happen if your pack is too big, and it's actually a pair of two smaller packs, or your pack is too small, and it's a small scalar array. In this case, if we are doing this, you will end up creating far too much temporary emulated packs, where actually what we want to do, well, if I'm a bigger pack, I can just call abs value on each sub-pack and call it a day. I don't need to build a new emulated pack and compute something bad where I can just unroll the actual SIMD operation on each of the half. And same for the scalar emulation, it's faster than just unroll the scalar operation on every piece instead of trying to generate intermediate emulation stuff. So we can actually know if I'm dealing with an actual pack or something which is emulated. So we have this flexibility through these dispatch things, which let us write the code in a way that, for some cases, we know we have the minimal amount of overloads, depending on the architectures. And the last stuff we do with that is this shuffle optimization. As I say, shuffle on some architectures is a very complicated base because it doesn't want to let you to do arbitrary shuffling. It has a very different set of patterns. And as I say, let's just have a look at the SSE operation that would let you do. Well, you are a valid SSE permutation only if the two first elements of your permutations refer to the two first, for an element from the first vector you are shuffling from, and the two others has to come from the other one. So what we do is we take this permutation as a list of integers at compile time, and we try to see what kind of SSE operation I am. And if I am none, okay, I will just fall down to emulate this shuffling. So either I'm what we call a direct shuffling, that everything is in the correct way with respect to the arguments, or it's the other way around. And if it's the other way around, well, I can optimize it by putting it in the correct way and switching the order of the arguments. So we compute that at compile time. It's not pretty. And we have different, oh, that's for afterwards. And we know what's going on, and if we are in the correct way, we call the correct operations. Where is it? Yeah. So if I have a correct pattern, I can just call shuffle with a proper whatever. And same for the binary permutation. So either you are a direct one, so I can call shuffle PS of A0, A1, whatever the mask of the permutation should be. And if you are indirect, you just permute the stuff. Okay, so SSE, it's okay. I mean, yep.
So if you shuffle 8 pack with 8
yep.
and equals 8, do you recognize that, for example, you have pattern of 4 and the same pattern of 4 next to it or something like this?
Okay, so the question is what happens if I'm on an SSE machine, but I have a pack of 8? In this case, we have a common case that say, okay, I'm a bigger pack than what I should be, so I can take the pattern, do some operation on it, and I know exactly what to shuffle on each piece and merge them back. Yeah, we do that. Yeah. The only stuff we can't optimize is when you give me a completely arbitrary permutation that make no sense for the architecture you are on, and I'm forced to just pick the piece up. But wait, what if the pattern of shuffling you give me is something stupid like it's the identity? Okay, or it's just a broadcast, or whatever. I mean, it's something that you could have written by calling a very specific intrinsic. Well, we recognize those two. And what we do actually is that for every meaningful, okay, what about not writing crap? For every meaningful permutation that we know to optimize better than just calling the shuffle thing, well, we know how to capture it. So let's have a look at broadcast, which is rather easy, for some definition of easy. So what's a broadcast? A broadcast pattern is a list of index, and they are all the same. So what I write is a small meta function that say, okay, this is a list of index in the permutation. You have P and you have the other one. Can you check that the complete list of PS is actually equal to P? And if that's the case, you have a broadcast. The only case you don't have a broadcast is when you have a pack of 1, because pack of 1, I can optimize shuffling a pack of 1 in a very efficient way, whatever the permutation. So I just say, no, I mean, it's a pack of 1. Okay, thanks. Now we define what we call a broadcast pattern. And the broadcast pattern is just a small function object that represents the fact that I am actually a broadcast pattern, and the value I'm broadcasting is the P01. Okay. And I wrote a small function object that say, okay, guys, you are passing me a pack, and the pattern you give me as a shuffle is a broadcast pattern over index IDX. So let's just call the broadcast function, which it's itself optimized into its own implementation. And to check what I need to do, well, I'm taking my pattern, my list of integers, and I compute a tag for them. And the tag for a pattern that is actually a broadcast stuff is this broadcast pattern thingy. And these things end up into the hierarchy, the tag of the functor call to shuffle. So we use tag dispatching to recognize optimizable shuffling patterns. And if it's a pattern I didn't recognize, I go through the regular, try to call the actual shuffling function. So we recognize broadcast, identity, because it would be terrible to cast a function to just get what you already have. What do we have? A broadcast, identity, reverse, or interleaving and disinterleaving operation. Repeat is basically say you cut your pack in two, and either you have twice the first or twice the second one, and we recognize slide, which is basically taking the value and let them slide out of the pack. So all of those cases are potentially optimizable given a given architecture, because some architectures doesn't know how to write, let's say, a reverse fast. So we won't take compile time to check if something is a reverse, while the current architectures can't do anything with it. So now, with all of that gone, let's see what we can do in terms of performances. So first thing is, let's look at some basic function. And by basic function, I mean math function. So this is a bunch of functions run on an AVX, it's an AVX machine, on their natural range, okay? So what we compute is a number of cycles to compute a single value out of the cosinus, log, or whatever. So which means that when I say that, so STD is a standard implementation. So 46 for X means that on this range, in average, I'm consuming 46 cycles to compute a single float output. Scalar is the scalar implementation provided by BoostSIMD, because we need it. It's a bit faster, not that much, but a bit faster. And so what does it mean 7 for the SIMD cases? That means that if I have a pack of, so AVX is 8 floats, I'm computing 8 floats at a time, and the time I spend computing one is 7. So 7 times 8 is what? 56? Yeah, something like that. So I'm actually spending 56 cycles, but in this 56 cycle, I compute 8 floats. So if I do the division, I got up to 7. So we are down to 5 for log, 33 for arc trigonometric function, and 6 for cosinus, but that's an old number. I think we are more close to 4 or 3 right now. And we have this thing, restricted cost. Sometimes you're dealing with value, especially for those kind of functions, which are periodic, that actually fits into a very narrow range. For this minus p over 4 is something that when you have some stuff that give you the angle of the wheel or whatever, there's a lot of sensors that give you this value. So it happens that if you knew that your cosinus input is between this far smaller range, you have a far faster implementation of the cosinus, which go down to 1.3 cycle. Same for the other function. And how does it work? Well, every function in BoostSIMD is a function object. And those things is what we call a decorator. So we can decorate function, and it give you another function with a modified behavior. So you have restricted, you have something which is called row, and row means that I know that if this function exists on these architectures with a single intrinsics, that may or may not be perfect. It's not perfect in terms of precision, or it doesn't handle 0 or minus infinity or whatever. I don't care. Just give me the result of these intrinsics. And you have pedantic that say, I actually care about vectorizing this code, but this piece of function call, it really, really needs to be careful about handling corner cases. So I'm willingly sacrificing performances to get the correct results. So you have this continuum of settings that you can apply locally on functions to get a slightly different function. So there we are saying that we know that our input are fitting between this. So we get the faster cost. What happens if you fill something which is not inside this range? Well, depends. Usually it's undefined, we don't care, that's your fault. And sometimes you get none. So it actually indicates you that you did something wrong. We are moving to a world where we always try to find an implementation which is faster and gives you none when you're not happy with the results. And we have discussion about having something like assert restricted that says that if you are outside, you get an assertion. That's something we can actually apply a lot because that's cost us nothing to implement, just a wrapper around the function object. Okay, single functions. What about actual, oh wait, I was about to say actual application. That's a good old fractal generator or whatever. This is actually an interesting stuff because it's mostly compute-bound operations. So it's close to no memory access. So if we are not fast on that, well, we lose globally. I mean, this should be the fastest stuff we can do. The problem with that is that the work you have to do on every pixel depends on the pixel value. So usually the scalar version of this code starts with a while loop that ends up either because you converge to the pixel value or because you hit the maximum amount of iteration. How on earth can I actually vectorize something with a while loop inside? Well, you just do it, actually. So this is the core of the function there. So I got my A and B value, which are my complex coordinates. And I have this do while, like in the scalar codes. So we got this x squared plus y squared, blah, 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 and so on and so on. These are convergence functions. But what can I do? Well, you can say that if I compute a pixel, I stop when I converge or I'm done in terms of maximum number of iteration. But what if I compute 4 of them or 8 of them? Some may stop before the others. So what you will do is stop, or actually continue, as long as any member of the pack has not converged. So what you do is you compute this mask, okay, and this computation of is x squared plus y squared lower than 4 gives you 4, 8, 16 logical value. And you say that, well, as long as any of the mask is true, it means that somewhere there is a value in the pack that still needs iteration. So I will keep going. But if I do that, I don't want to increment the values that already converged. So what I do, I use the mask to just say, okay, just increment res only if the mask tells you that you need to be incremented. Okay? So this code works I think if you feed T, which is a pack, it gets vectorized. If you feed regular float, it gets run too. So you can actually use the same code for both the SIMD and the scalar parts. And so for a while, people were actually bitching about because we were writing the benchmark, so we were a bit biased. So I just grabbed a result from a paper from somebody else that was actually using BoostSIMD and a lot of other solutions for auto-vectorization, okay, on this exact algorithm. So it's not even us that did the numbers. And if you look closely, so we are the first over there. So we got a speed up of 3.2 in SSE4 for thousands maximum iteration, which is competitive with stuff like ISPC or it's a bit better than OpenMP in a SIMD mode. And well, we're pretty much okay. And on AVX2, we're basically a bit better, but not that much, than actually writing the stuff using intrinsics. We are on par, a bit smaller, but on par with ISPC, and a bit smaller, but on par with VC, which is another similar library. So we are pretty much where we wanted to be. So we wait up a speed up of 4 for SSE and 8 for AVX. So we are at most at 6.9 there and 3.2 over there. So we are pretty much where we wanted to be. So another stuff is Mario Mulansky wrote a couple of years ago now, wrote a version of ODE that can work with BoostSIMD and use it to vectorize a roster system resolution. So I didn't write anything. Okay, you can play with it. It's something there on Mario GitHub. Well, how much stuff did it change? Well, nothing there. That's the actual stepping function. Doesn't change anything. So you see that multiplication, random operation, and that's the way he was vectorizing. So the scalar code is up there. So the state type is just a vector of double, and you call whatever. What do you do when you want to vectorize it? Well, your state type is just a vector of pack, done. Okay. You just change that, and you have to change something else, which is computing how many elements you want. So if you have n, you probably want n divided by the actual size of a pack of double. Done. What do we get for that? Well, we get a nice 3 times faster on the Xeon, okay, and a bit less than 2.6 on the 90 Opteron. But you just have to change the type in the frigging vector of states. Done. 3 times faster. Finally, this is something we wrote. Sorry for that. It's a motion detection algorithms. So you got a video stream with stuff moving in, and you want to detect where stuff are actually moving. It's a very trivial task. You could actually write something that just takes the difference between 2 successive frames, and you apply a threshold. If you do that, if you have an image where the contrast in some regions are widely different, you may miss movement in those high or low contrast zones. So another way to do that is to apply an algorithm which is called sigma delta, which is basically, okay, math, modelize every pixel intensity as a Gaussian mixture. And so whenever the pixel intensity is bigger than 3 times the sigma of its Gaussian, it moved. Well, it sounds complicated, but in fact, you can write a code with this using integers only, and it's probably like, I think, 6 or 7 lines. But it uses small dynamic integers, 8 and 16 bits, and you have a very, very low arithmetic intensity. So can we actually get speed up on that? Well, the code fit in a slide. So again, we play with mask. We have this muless thing, which is a saturated multiplication that help us not requiring casting to a bigger integer types, and so on and so on. We have this complicated if 0 else all bits functions that do what's written on the can, that if the condition is true, I give you 0. If not, I give you all bits set to 1. So what kind of performance do we get out of that? So whenever, okay, so different size, okay, so the green one is the scalar code compiled with GCC with every optimization on. We basically have something like 150 something frames per second, okay? There is a times 10 power of 4 up there, okay? When you trigger the same code using BoostSIMD SSE2, we got speed up of 3.8, okay, up to 6.6 there on 8-bit integers. We got a 6.7 for AVX that doesn't have integer support, so we fall down to emulating it using a pack of SSE integer registers. And when you kick on AVX2, we got a speed up of 26 out of 32, and we are around 27,000 frames per second. Okay, and it goes down because at some point we start trashing the cache and whatnot, regular stuff. So conclusion. Well, you can actually write something which is written in C++11, use modern standard idioms like standard range, operation, algorithms, and you still get performances. The exercise was, how much can we shove into this before it breaks? We show that we can actually have a lot of SIMD-specific items inside without it breaking. Well, let's say it this way, because that's the joke with this slide usually. So we made the first talk about BoostSIMD 4 years ago, or 5 years ago now, at the first or second meeting C++. And back in the day, it was available soon. Now it's available. So you can go there, play with it. We even have documentation. Woo. And I need to fetch Michael Kess or someone over there to go over and actually make the planification of the actual review for integration into Boost. But currently, you can play with that. We have a bunch of tutorials. You can actually tell us if something doesn't work. Probably will. Or not, maybe. If you have question, whatever, just go onto our issue tracker, and we'll be happy to answer you. So I will just make a big thanks to all the guys in the BoostSIMD teams that work on that, especially so Charlie, which is the lead developer of the new version, and all our co-workers, and a bunch of big thanks to people like Tim Lechman, which was our earliest adopter of the technology, Serge Gelton, which works on Python, which is a Python to C++ compiler that use BoostSIMD to optimize the code, Mario for its work on Boost AudioInt, and a couple of other friends and co-workers that are actually testing BoostSIMD in crooky situations. So thank you for your time. If you have any question for the bunch of time, that's best. Thank you.
Okay, one quick question.
It's basically a follow-up to my earlier question. Is there a way to get support for multiple hardware architectures, or say I have a program that is supposed to run on Windows, but I don't know exactly what kind of process it's going to run on. Can I build in support for multiple SIMD implementations?
At runtime?
Runtime dispatching,
okay.
yeah.
So if you need runtime support for different architectures, what we actually suggest is doing things like this. So basically what you do is, where is it? Okay, internet. I should have went to the page before, that's my fault, okay? Yeah, so we have a real tutorial about that. Basically what we tell people is you write your kernel in a function with interface has to work with raw data pointer. You should not use pack in interface of functions that may change depending on the architectures for obvious ABI reasons. And you pass this BoostSIMD default site magic macro as the last parameters. You write your code into this, and what you do after that is somewhere in the header, you just declare the prototype for the architecture you are interested in supporting. So there we put all of them just to showcase, but if you need SSE2 and AVX, you have just those two. And we have objects that basically bear the name of the architectures that you can use doing, okay, is AVX supported? Then yeah, I'm just calling compute with whatever data using AVX. And what we tell people is to build large kernels this way instead of switching at every function for performance issue. But we support this thing like that. You can either compute everything in a single binary if you want, or you can have different dynamic library for every architecture, and you can play with that around.